Today I'm gonna continue onwards in terms of implementing more uh, a more sophisticated bounding volume for rotating objects. In the last episode, I ended up spending a lot of time doing different stuff in terms of basically understanding what was going on when I recalculated the bounding volumes. So, yeah, as this code kind of suggests, I did a lot of different stuff to test out what was happening. I didn't understand why I was required to recalculate the bounding volume from an instance of the original bounding volume. And it all had to do with me not understanding entirely how translation between local object space and the world space happens. And yeah, therefore I ended up in a situation where we actually made some mistakes. But we are currently at a state where I have these issues resolved, and I think I have a fair understanding on what we are doing. So yeah, the current OBBs get simply just updated in terms of their center positioning, which is in world space and is driven by the physics component. I also realized when I was contemplating what uh, caused the issues that I have a lot of different ways to specify a position in terms of world space. Um, and we definitely want some cleanup of that code uh, sometime in the future. So yeah, I cleaned up this code. We're simply using the bounding volume, updating the bounding volume center. I also moved this part of the code where we update the the bounding volumes and the transform until after we did collision checking for what will be the previous frame, and then uh, and then we do uh, let's see, we do update the positions, and then we recalculate, for instance, the matrix and the bounding volumes afterwards. And I'm not sure it is gonna stay that way, but um, yeah, um, yeah, I'm wondering when to update the information, because yeah, I would prefer not to update these data structures more than once, even though, no, it's not only a copy, it's actually a calculation of the rotation matrix from the quaternion. So yeah, at least this is just a basic copy. I guess you could, since it's a basic copy, you could get away with storing the data before and after, and but then again, this is driven by the position. This is driven by the rotation. Yeah, I think you could do it in different ways. Yeah, you could do it in different ways, I think. But anyway, let me clean up this. and move a lot of this stuff. So as a proof of concept and to show that I now understand how to calculate and update bounding volumes. This code got implemented. Let's see. Let's move this out. Just gonna cut and move all this. Just doing a bit of cleaning here. So yeah, after I figured out how everything works, I did a debugging section. So basically, we want to show where the minimum and maximum corners of this bounding volume is after it got updated. So basically we grab the center and then we grab the rotational axis of each part of the local coordinate system, meaning that how do we transform from local object space into world space. This is actually the matrix for that. This is getting calculated exactly from the world transform matrix. So this is actually not needed. It's just a step along the way. And yeah, you basically offset the half widths, or rather not offset, translate them by the rotational and translational parts of the world transform matrix, and you are able to simply calculate the new minimum vector and the new maximum vector, or rather the min and maximum vectors from that. And since we have a system here that allows us to draw rays, we can actually call this every frame and draw two rays, which are going from, well, this is going to be the same ray. Anyway, so this ray will go through the center of the object and should follow along the object's rotation and translation in world space, meaning that this is the world space minimum and maximum coordinates. As you can see here, whenever we tested it out, we see that I drew a line from the maximum corner to the minimum corner of this bounding volume, and whenever I rotate the object, the minimum and maximum actually gets drawn and represented by this ray that is drawn through, or rather from the minimum to the maximum. So this is the oriented bounding box, and this is the ABB. So as you can see, our calculation actually follows the object in terms of rotation and translation. So now we are able to actually calculate the bounding volume correctly. We have transformation from object space to world space, and everything works as intended. This means that now we can look into actually doing uh, collision checking with oriented bounding boxes. And that is what we will implement um, in this video today. We will, I'm just gonna close some stuff here so I don't have to scroll as much. Anyway, so yeah, we want a version of our collision checking method here, which takes OBBs instead. We actually want sort of a copy that checks dynamic bounding boxes against static bounding boxes and collects the indices for whatever static bounding boxes we collide with. So yeah, we're going to implement actually a placeholder for this. We're not going to disable the old system before we have an alternative. And the method will be yeah, the method here, how should we structure it? I don't know. Anyway, collisions. Now we have a different name, and we will also have a bounding OBB instead. And we will, for now, disable this old code. And let's see, we check against our ABBs with a half width and a center. Eventually, when the old type of ABBs gets discarded, we will rename these data structures. But yeah, so we will do a separating axis test. We will basically treat the ABB as an OBB and test along the 15 axes. Axis. Well, I don't know how it's properly pronounced actually, but yeah. We will do that. We can do a bit of optimization, but maybe we just go through the whole algorithm. So the separating axis theorem is a way to handle collision checking where you the theory is that if you can find a separating axis or a plane between two objects, they can be colliding. You simply take each face of each object and project them pairwise onto a perpendicular vector. And if the distances between the centers of the objects are within a certain range, typically too small compared to the respective radiuses, radii, I think it's called in plural. If it's the distance between the centers is smaller than the radii combined, you would know that you would realize that there's a collision. So yeah, that's the theorem in terms of doing collision checking. Yeah, so that's what we're gonna do. And for us to do that, we want to store two floats. radius A and radius B. Let's see. And we will actually calculate a matrix. I don't know if I implemented rotational matrices. I think I did. It's a 3 by 3 matrix. Since you simply store the local coordinate systems, which contain the actual rotation of the x-axis, the y-axis, and the z-axis. Yeah, I do have a way to store rotational information, and it's accessible by the parenthesis operator. Yeah, so I think we will just use that struct. It's not optimized, and you could do SIMD optimizations on a lot of this code. Yeah, we're not going to spend time doing that. I'm at least not in the mood. We do a lot of SIMD here, and yeah, as fun as it might be to learn about optimizations on a really low level, yeah, I'm kind of too tired to do a lot of that. Anyway, so we want the radii of each object. We want a G-float 3 by 3, which is going to be our rotation. And let's see. And we want the absolute rotation as well stored, meaning that it can't be negative. This is a fairly complex method, and I have to say that I'm not uh, uh, some kind of mastermind. I have to read books to understand a lot of it, and I usually try to get to a point where I'm certain how everything works. But yeah, I am not entirely sure always. Anyway, this is uh, a way to calculate the rotation of uh, one object into another object's rotate, or rather local space. So we would like to take each object, static object, and translate it into the local space of the OBB. Yeah. And this is where you can actually do some optimizations. You could, yeah, we will have to hard code some of our um, our data here, since you are supposed to take the vector dot product. Let's see, vector3 dot product between the OBBs um, axis number I, which is the starting with the x, and get the dot product of the static objects are um, first the x-axis, then the y-axis, and then the z-axis, and then you do it all over but you just shift to the y-axis of the dynamic object and do it again. We will create a vector array here, ABB axis. I don't know, axis. How do you pronounce the plural one? Anyway, if someone can help me out, how to speak of one axis, more axes, axes. Yeah, let me know. Anyway, we create an array of ABB axes. Yeah, the x-axis, the y-axis, and the z-axis for the ABBs, which we already know will be these vectors. I mean, the x-axis is going to be like this, and the y-axis is going to be like that, and oh, rather, I'm not doing the y-axis yet. I'm sorry. And then the y-axis is going to be like that, and this z-axis is going to be like this, and that will be the same for all static objects. So we simply do the dot product, and of course we have to grab just one of the components, since all 4 slots of this register gets filled with the result of the dot product. As you can see here, we simply call the intrinsic dot product, which fills every part of the yeah, every part of the register with the result of the dot product. So we calculate the rotational matrix. Actually, we could just store this because it would be the same, and thereby we don't need to calculate it every time. We would like updating of the radii. Yeah, we do this pre-computation, so instead of doing it for every object, that sounds more reasonable. Then we compute the translational vector. This is something that we need to do every time. Translation, and we will take the vector of the OBB and subtract the center of the static object. And then we have to change the translation of these objects into the space of the OBB as stated before. We want to set the translation to Let's see. Yeah, we could do a method where we build from maybe we could use let's see, do we have a function that builds? Yeah, we could do extract the x component of a dot product, which will be the same, the y component, and then the c component. This builds a vector where we take the dot product of the x, the dot product of the y, and the dot product of the v, and puts in a last component. We could also do a version here where we do dot 1, dot 2, dot 3, and then delete the last one because we do not need it. Build vector 3 from 3 dot products. So we unpack the lower of the first two vectors and interleave them. Then we take the third vector, and then we just let's see, the vector zeros sets 0, and then we put in a 0 at the last part of the register. Yeah, we can do this and simply pass in 3 dot products, which is we need to translate the x component, the y component, and the c component in respect to the rotation of our OBB here. So the first component is going to be the math dot product of our translation and our x-axis. Yeah, this guide says something. Let's see. I'm not sure if it's correct. I'm not sure if it's correct. Yeah, I think this is supposed to be something else than stated here. Let's see. We do the first one like that. Then the book actually says this is supposed to be 2, but I think that's a mistake, but what do I know? So I'll second component might have to be 2 instead of 1. It doesn't make sense that you translate the C component or rather translate the Y component by the C local coordinate anyway. Um, so yeah, The next part here is also something that we can do outside the for loop here. Actually, we're just gonna do this and fill in the absolute rotation structure with exactly the absolutes of our rotation and plus the float epsilon value. This is a way to handle cross products that are near zero but not are actually zero, meaning that you might, because of rounding errors, end up interpreting something that is not parallel to being parallel. So adding a small number kind of gets gives the algorithm more stability. We might want to calculate also a half width here. Yeah, we might want to transform the radii of the rotated bounding volume. Right now I do not store them. I guess you could do that outside the scope of this, meaning that we could do it in here. We store the rotation. Yeah, we might want to update the half widths as well by simply translating them. Vector matrix, vec3 matrix, multiply matrix. So we take the half widths and pass in the matrix of the transform. We store them for later. Then inside our debugging here, we should simply pass in these instead. Let's see if everything works. Oh no. Yeah, that definitely broke something. And maybe we want to store the original half widths and not apply the transformation. Let's see, this is going to keep it as it were. And this is then the new one. Let's see. Yeah, for the first comparison. Well, yeah, I think we apply the yeah, I think the half widths are not rotated. I mean, it's just when we want to calculate a point from them that we apply the rotation to the half widths. They themselves probably do not change. It's only when we have to view them in world space we have to transform them. Yeah, so I think we are just supposed to test for the regular axis of the first let's see the OBB. So we take the dynamic object and we take the half widths and we take the first component in this instance, or rather first we take the x, then we take the y, and we set the radii of let's see, static objects here. This is not going to work. I is already in use. Let's do a J. Or rather, maybe just do an O here. O is equal to that. O is like that. And O is meaning that uh, yeah, we do it like that. And then we can use I all we want. But it's of course the O we want here. And the radii this is going to be the first component rotated over the current axis plus the exact same thing. Instead of that, we just want the y component and rotate that with respect to the y component of the local x-axis in absolute terms. Yeah, if it sounds convoluted, it's because it's kinda it kinda is. And then Oh, wait a minute. We do O. And let's see. I somehow messed that up. It seems I broke something. Anyway. Then we check. Let's see, we could set a temporary flag. Double continue for loop. Yeah, we could do a go-to, it seems. Do we want to go to... let's see, how did we handle it before? Yeah, but it's inside the for loop, so continue won't work. Yeah, we could implement this as separate code. I won't mind doing the go-to version. Go to continue to. Okay. So if the absolute value of the translation for I, or rather the translation I component, meaning X, Y, or Z, is greater than radius A plus radius B. We go to continue. Second. Let's see, we create a scope here. Or rather, will this actually work? Yeah, if we do it down here. Yeah, we will skip the collision registration. And it will continue anyway, so... Okay. Then we check the local axis. Once again. And we will set radius B to that. Then we will set radius A to something like the exact same thing, it seems, except for yeah, we will simply swap these around and do the dynamic object instead. And of course we do not need the O. Yeah, O is a really bad letter, I think, to do that. And then we check. But we check for something. Whoops. That's a mistake. We have to take the absolute of not all values, but like that. We also need to do like that. And we want the absolute of the translation X component, the times the rotation. Plus the translation for the Y component. There we go. Let me just do this and print. Now we can, yeah, wait a minute. We have here. We print out what object we collide with. I know we're not done yet, but I just want to test these two different axes. Of course, we need to yeah, okay. I kinda, yeah, there we go. I introduced something not so nice. We do some collision checking here. Let's just do a fake one here, since we won't be fake. Since we won't be overwriting the old method just yet. We want the dynamic bounding volume. We got dynamic bounding boxes OBB. We want to test it against that one. I think that. Oh, wait a minute. I haven't created it in the header yet. There we go. Okay. Yeah, we collide with the floor right now. It says, let me just remove some of this debugging information since we don't need it right now. So yeah, our rotated bounding volume is colliding with the floor, which is great. And this is colliding both with object 1 and object 0, meaning this wall and the floor. Can I hit it? Yeah, now we move the object so it actually probably interpenetrates a bit with, yeah, you can see the edge of the object there interpenetrating. That's great. So yeah, something is working. What if we yeah, we calculate the penetration depth from the old volumes. Yeah, so we also need to do that. But the separating axis test is not actually done yet. We're only testing over the first 6 axes of in total of 15 different axes that are possible when you're checking for 2 boxes which can be oriented in whatever way. I mean, we know this is an ABB, but we can only do optimizations in terms of what the relative rotation of the local coordinate system translated into the OBBs coordinate system will be. Yeah, so we need the last tests. And yeah, we will implement those, and then we will maybe later today do a method where we kind of test if we can get a penetration depth, and at which point we actually have a penetration of the two objects. Yeah, but we're getting some positive progress here. Let's see. The next test here will be the half width on the y-axis, absolutely rotated by the apparently. Yeah, so you kind of create a plane between the z and y axis of the first object. Or it's the translation maybe. Well, yeah. I should definitely dive into this algorithm a bit more in terms of understanding the left axis comparisons. I mean, this is fairly simple. First, you take the OBB and orient every axis around its local, or rather its rotation in world space, and then you compare if the projection of the center distances of the two objects is smaller than the radiuses of each object combined along this specific axis, which is what happens here if we have a distance between, or rather translation between the two object centers that is greater than on this specific axis. This is the x-axis, for instance. Then we can be certain that we do not have a collision. Yeah, but the last parts of this code here, I'm not extremely confident in how to interpret, so I'm just gonna type it out. And we calculate the radius of B, which is kind of the it's actually the cross product of the two axes. So it's the cross product of the x coordinate vector of A crossed with the x coordinate vector of B. So this is basically a cross product. All right, and you actually do it for all combinations of different axes. So first you compare the cross of the x-axis, axis, and blah blah blah. I still don't know how to pronounce it. And then you check the translation version of that and compare it to the radiuses. So yeah, we calculate the radiuses for each part of the local coordinate system of each object. So the next one here is going to be the static objects. And since we're comparing the x-axis, yeah, we do like that, and then we just check if the absolute value of something is greater than radius A plus radius B. And the thing we test is the translation, C coordinate rotated by the rotation of the first part of the calculation, or rather this part of the calculation minus the translational y-axis rotated over, oh, not y. Y represented by a 1. Whoops. And then we do the same for the next axis. Let's see. This is going to be this part of the axis, and this is going to be let's see. And I imagine the next part is some iteration over that. Yeah, we check this, and we check this, and then this is going to be 1. And then 1, 2 minus 1, 2, 2. All right. Mm. That's the first three. We have several more to go. So we start out with maybe 0 here, maybe 0 here, 2 zeros here. And then we take the Y. The C here, 1, 1. Then we take the X. I'm just gonna type in all these tests. Then the comparison here, 0, 2, 1. And then maybe a 2 here, or not maybe. We will pass in a 2. Okay, 0, 1, 0 here. 1, 0, 0. Once we're done with this, I'll have a break. E1, and then 0, 0. And then 0. Swap these. Alright, the last two. 0, 1, 1. 1, 0, 1. 0 here, 2, 2. It's still a 2. And then that's a 0. And then a 1. And here. And 1, 1. And then the last one. All right. I think that should be it. Yeah, let's try that. So we definitely have a collision with the floor. Sometimes it seems like so we're not colliding with it. Let's see. Yeah, now it overlaps. Definitely. And the floor doesn't overlap. Now it overlaps with the floor. Great stuff. Then we overlap with the and if I push it up here, we overlap with all three. Yeah, I think this actually might work. It definitely detects the collisions, it seems, whenever the minimum or maximum, or you'd imagine that the minimum or maximum, which represents the corners of the boxes, actually collide. Yeah. Exciting stuff. Exciting stuff. All right. That is pretty nice. We simply ended up with a system that can detect collisions between OBBs and ABBs. As you can see, whenever the whole thing separates, it doesn't collide with anything else but the floor. As you can see from the console in the background, whenever the object rotates in such a way that it collides with, as you can see, it's entirely stuck inside the wall here, which the collision system correctly recognizes it as a collision with the floor and the wall. If we try to separate the object, can I? I can't make it bounce because I just reduced the. Yeah, but yeah, the collision with the end wall is not constant because the object sometimes rotates into a place where it's not colliding. Right now it is colliding, but now it's not colliding with the floor, which actually makes sense if we look at the object. Right now it's rotated in a different orientation, and sometimes when we, yeah, I think this works pretty good. Oh, we're getting close to collision with the floor. Do we end up with it? I don't think so. Oh, yeah, maybe. Oh, yeah, the box is oriented. So, yeah, probably one of the corners. I mean, whoops. One of the. Oh, I fucked the camera totally. Oh, excuse me. Um, I'll have to be right back. All right, but that will be it for now. I think let's just see. No, it obviously doesn't detect collisions on objects that do not collide. This could be moved into a more generalized method of checking ABBs or OBBs and OBBs. Um, I said a lot of letters there. I mean OBBs versus OBBs or OBBs versus AABBs. Uh, this is obviously a more efficient method of comparing OBBs to AABBs, since we know that every axis for the AABBs are the exact same as we set up here. But this is great stuff. So the next thing will be to take this part of the code and then maybe just do exactly the same thing here. We want to calculate some contact normal of the collision. We want some penetration depth of the collision, and then we want to resolve the collisions. This part shouldn't be updated since maybe it should actually. Let's see. Yeah, I think this is more for particles, so this will follow along afterwards when we have more a complex collision resolution in place. Yeah. I'm unsure whether we actually want to calculate the penetration depth or not. Or whether we want the physics system to handle it in some different way. Yeah, I'll figure that out. But at least this was a really nice step along the way towards a more complex physics system with rotations of our objects. We're moving from only basically working in oriented planes, axis aligned planes, I should say rather. We're moving towards simply just oriented objects which are allowed to rotate in space. Let's see, I actually want the debugging for now, so let's not disable it just yet. I mean, the array is absolutely amazing in terms of debugging what's going on. Let's see, I'll just see if we start to get any noticeable effect on our FPS if I don't know if I enabled tearing. No, I haven't enabled tearing. Let's do that as well. Yeah, so I'll have to copy over some models here because I updated the character model used. Let's see, because there was some problems. I ended up setting the origin to the base of the object, and that really just makes everything look weird. Oh, I didn't have to frame capture here. I actually didn't want to frame capture. Okay, okay, disconnect. Okay, we can still spike upwards to several thousand frames per second. And this is without any optimizations. So we're not really spending a lot of time at all. Not even 1 millisecond. Which is great. And we are still able to do a lot of different optimizations. Do I not actually draw the rays anymore? Oh, the rays get replaced by the lines here. We draw too many lines too fast. 1/3 of a second sometimes. Yeah, and this is, as I've said, without any optimizations in terms of frame rate. So I think we're fine for now. But we would like more sophisticated collision checking in terms of space partitioning and so forth, but we will implement that in the future. First, I will create the part of the physics system that actually handles collisions with rotations more actually just handles collisions with rotations. So yeah, that's the part of the work we're doing now. Hopefully we could end up doing a lot of it over the weekend, and then we could look into whatever we want to do next. Maybe some reorganizing of the code or optimizations, or just simply some gameplay mechanics. Yeah, I think gameplay mechanics is a priority. And maybe a HUD or UI. Yeah. But once we get the last parts going in terms of the collision detection, and or rather we already have collision detection in place, at least for one OBB. Then we will do calculations towards collision resolution with torque and yeah, just object reorientation. We will also do something called contact planes, or rather contact points, which are the points of contact between two objects, which we will use to kind of store whether an object has several contact, or rather two objects have several contact points that are needed for a collision resolution. Yeah, but anyway, that's a lot of blabbering on what we're going to do in the future. This is it for now. Thanks for dropping by or hanging out. Feel free to comment, like, or subscribe. Follow on Twitch or YouTube. Even if you want to support the channel, feel free to do that. That would be amazing. Yeah, but hopefully I'll be seeing you